Our next speaker is Margot Fitz Axen from the University of Texas at Austin, whose field is astronomy. The advisor is Stella Offner, and has participated in a practicum at Lawrence Berkeley National Lab in 2021. The title of her talk is The Impact of Cosmic Rays on Molecular Cloud Collapse and Star Formation.
All right. Thanks everyone for being here. And thanks for the introduction. So I'm going to be talking about the work I've been doing for the past few years of my PhD, running numerical simulations of star formation with cosmic rays. And so I'm going to begin with some of the introduction to some of the astronomy concepts I'll be talking about for all the non-astronomers in the room. So I'm going to start with star formation. And so star formation begins in molecular clouds, which are these big clouds of molecular hydrogen gas, about 10,000 to 100,000 times the mass of our sun. And these are the coldest, densest regions of our interstellar medium. And so in general, they're supported against gravitational collapse by turbulent and magnetic support. But the turbulence in the clouds also creates these dense filamentary structures, which host gravitationally unstable cores. Whoops. And these cores go on to collapse under their own self-gravity and form an accretion disk surrounding a central protostar. And these protostars inject energy and momentum, this is what we call stellar feedback, back into their parent molecular cloud, further influencing the star formation in the cloud and eventually dispersing the cloud. These are things like protostellar jets, powerful stellar winds, radiation, and supernovae. And so you'll notice I put the length scales of these as well. So this entire process from the size of the cloud down to the size of the accretion disk and protostar spans about 5 orders of magnitude in both mass and length scales. And so this makes these numerical simulations of individual star formation challenging because we need to simulate this huge span of scales in magnitude down from the size of the cloud down to the size of the stars. And so it's really only in the past decade or so that we've gotten really good numerical simulations where we can model the formation of individual stars. And so one of the groups that's been doing this research that I've been working with is called the StarForge Collaboration. So this is a multi-institution collaboration developing these numerical simulations of star formation to answer some of the open questions we still have about star formation, like what is the mass distribution of stars and how do forming stars affect their environment. And so what's really crucial about these simulations is that they can resolve all this necessary physics, like all the stellar feedback, and resolve individual stars. And so I like to show a picture, sorry, it's a kind of a bad resolution here, but this is a snapshot of the projected density from one of their simulations. So you can see the full molecular cloud outlined there in red, and you can see the filaments kind of in yellow there. And you can see the points there are the forming stars. So even though we've gotten these really good simulations of star formation, they've still simplified some areas of physics in order to make them more computationally feasible. And so one area of physics that the StarForge simulations and all other simulations of individual star formation have simplified in the past is cosmic rays. And so cosmic rays, to introduce this to non-astronomers, these are charged particles like protons, electrons, and ions, and they travel at relativistic velocities, and they gain these relativistic velocities in shocks at high energy locations, high energy phenomena in different things like supernovae and stellar winds, AGN, things like that. And so in the Milky Way, we know that the cosmic ray energy density is around 1 electron volt per centimeter cubed. And so this is comparable to other things like starlight, radiation, magnetic fields. So they're quite an important component of our interstellar medium. This is the energy density, about 1 electron volt per centimeter cubed in our solar neighborhood. But we know that the cosmic ray energy density varies throughout the Milky Way, both on large scales and small scales. On average, it varies between about 0.1 to 10 electron volts per centimeter cubed, but there are regions with more cosmic rays and less cosmic rays than that. And so cosmic rays have an influence on a number of different things. They influence gas temperatures, ionization, and dynamics. And so the way they've been treated in astrophysical simulations, like the StarForge simulations, the easiest way to treat a quantity in simulations is, of course, to hold it constant spatially and temporally. So, for example, the StarForge simulations in the past just assumed a constant cosmic ray energy density of 1 electron volt per centimeter cubed to calculate the temperature and ionization state in the gas in these star formation simulations. But due to their importance and the fact that we know that the cosmic ray energy density varies, many simulations have actually evolved the cosmic ray distribution along with the gas. So for example, these are a couple snapshots from the FIRE suite of galaxy simulations. And here you can see there's a projection of the gas density on the left and the cosmic ray energy density on the right. And what these simulations have showed us is that cosmic rays really play a huge influence on gas dynamics on these large scales. And they do things like they drive galactic outflows and influence the gas in these different parts of these simulations. And so, despite this, no previous simulations of individual star formation have included a cosmic ray transport method to model the spatial and temporal variations in the cosmic ray energy density. And so, yeah, that's been what my PhD project has been on, is coupling these StarForge simulations for star formation and adding in an explicit cosmic ray method, a transport method, in these numerical simulations of molecular cloud collapse to address these questions. How does the cosmic ray distribution in the cloud evolve? And how does it impact the cloud evolution and star formation? So just to go into some of the methods. So the code that we use for these simulations is Gizmo, which is a massively parallel multiphysics code that includes magnetohydrodynamics, gravity, radiation transport, cosmic ray transport. And so, yeah, Gizmo has been used for a number of different astrophysical simulation applications. And it includes a set of packages for star formation, and that's basically the StarForge project. And these include all the additional physics necessary for star formation, so like the stellar feedback, and it includes the formation of individual sync particles where the actual stars form. And it's a Lagrangian code. And here's a couple of equations that I don't want to go too much in. But I just wanted to say something briefly about how we model the cosmic rays. So we don't model the individual cosmic ray particles, but we evolve them as a relativistic fluid along with the gas equations. So here we've got two coupled equations for the total cosmic ray energy and flux. These are also coupled to the gas equations. And so I just want to add, this is a set of two moment equations, and it's very similar to how moment-based methods are done for radiation transport, if any of you are familiar with that. And so, yeah, so just for example, if we have a simulation cell and it has gas properties like the gas density and velocity, then there's also cosmic ray energy and flux associated with that. And so for our simulation setups, we start with this uniform cloud of gas, 2,000 solar masses in a less dense medium, similar to all the previous StarForge simulations. And we run a number of these different simulations with different variations. The ones I'm going to talk about today are we run a fiducial simulation starting with 1 electron volt per centimeter cubed. For the initial cosmic ray energy density, so that would be similar to a molecular cloud with our solar neighborhood value. Then we also run one with 10 electron volts per centimeter cubed. This would be a region where we would have a high cosmic ray energy density. And then we run a simulation where we just fix the cosmic ray energy density at 1 electron volt per centimeter cubed and don't model the cosmic ray transport. So this is just the standard way previous simulations have done it, and we just run this for comparison. And so to give you an idea of some of the computational requirements, the mass resolution for this required to resolve the individual stars is about 10 to the minus 3 solar masses. So going from the size of the cloud down to 10 to the minus 3 solar masses requires 2 million simulation cells. And for the time stepping requirements, Gizmo uses an adapted time step to adapt to the different needs in different areas of the simulation at different times. But typical time steps in these simulations are about 1 year. And so each one we run for a total time of 4 million years to model the full evolution of the cloud and star formation. So that's on the order of millions of time steps. So yeah, these simulations each required about 5,000 node hours. And they were done on the Frontera and Stampede 2 supercomputers at the Texas Advanced Computing Center. Okay, so now I'm just going to talk about some of our results. And so I want to start by playing a movie. And so I'm going to play it, and I want you to first watch the projected gas density on the left, and you're going to see the formation of the stars. And so you see the cloud collapsing, forming filaments, and then forming stars, and the feedback then blowing the cloud away. And I'm going to play it again so you can watch the cosmic ray energy density. And so yeah, I want to just highlight a couple key things that we found. So the cosmic ray energy density, we found very strong energy losses for most of the cloud evolution. So up to around 3 million years, the cosmic rays lost a lot of energy due to certain properties of the cloud, causing them to lose a lot of energy in their transport. So for most of the cloud evolution, you can see that the cosmic ray energy density in the cloud is very low. But then at around 4 million years, this is when we start to get some of those very powerful stellar feedback mechanisms like the stellar winds. And these end up accelerating cosmic rays, so adding a lot of cosmic rays to the simulation, a lot of cosmic ray energy. So you probably saw these bright points in the cosmic ray energy density. And so yeah, so those are the two key points, is that we lose a lot of cosmic ray energy for the first part of the simulation, and then suddenly have these acceleration sources that add a bunch of cosmic ray energy. And so one of our results was that for our fiducial simulation, where we started with 1 electron volt per centimeter cubed, what we really found is that the cosmic ray energy density in the cloud was on average a lot lower than our simulation where we just fixed it at 1 electron volt per centimeter cubed and didn't evolve the cosmic ray transport. And so because the cosmic ray energy density was so low in the cloud, it actually had a minimal impact on this simulation compared to our no cosmic ray transport simulation. So here you can see the gas density of these two simulations at 3 million years. You can see it looks very similar. There's small statistical differences in the stars forming in these two simulations, but overall they evolved very similarly. And so if we look at our simulation where we started with a higher cosmic ray background of 10 electron volts per centimeter cubed, we found a similar effect with the cosmic rays. So they lost a lot of energy in the cloud, but we found that in this simulation, the cosmic ray pressure from outside the cloud was high enough, and the cosmic ray energy losses in the cloud were strong enough that we had this additional cosmic ray pressure outside the cloud, which caused the cloud to collapse faster and form more stars. And so here you can see the three simulations, again, at 3 million years. If you look at the one all the way on the right, that's our high cosmic ray starting simulation, and you can see that the cloud looks a little bit more compressed. It's got more stars forming, and the stars that are forming are bigger. And so one of the quantities that we like to look at in these simulations is what is the final star formation efficiency. Basically, in this cloud of gas, how much of the cloud ends up collapsing and forming stars. And so what we found is that the high cosmic rays simulation ended up collapsing and forming about 13% of its mass eventually formed stars, whereas our fiducial simulation only about 9.53%, and our no cosmic rays simulation about 7.35%. So yeah, that was a main takeaway, was that in this high cosmic ray area, you get faster star formation. And another thing that we like to look at is the mass distribution. And so what we found is that the simulations with cosmic ray transport have an elevated final median mass over our simulation with no cosmic ray transport. In particular, our fiducial simulation had a final median mass of 0.5 solar masses. And so, yeah, here I'm just showing finally a quantity that we like to look at, which is the stellar initial mass function. Basically, it's the number distribution by mass of stars. And I've highlighted there in red some of the mass bins. And you can see, if you look at the black, which is our fiducial simulation, compared to the cyan, which is the no cosmic rays simulation, you can see that some of those mass bins, like 1 solar mass up to 10 solar mass, have higher numbers of stars. And so that's what drives up that median mass. And we think that this effect may be due to the stellar winds at the end accelerating cosmic rays and changing the gas properties and somehow influencing this mass distribution. And so what we're really trying to do now is run larger clouds, because like I said, these were only 2,000 solar mass clouds. We did this so we could run a number of them and get some results. But what we really need is larger cloud simulations that form more stars, so we can get a statistically significant picture of the stellar initial mass function. So right now we're running simulations with about 20,000 solar masses to better constrain this mass distribution. Yeah. And so before I put out my conclusions, I just want to say a big thank you to my graduate advisor, Stella Offner, and my practicum advisor, Peter Nugent, the StarForge collaboration, and of course the DOE CSGF. And so I'll leave that up there and take any questions.